Welcome back. This will be our second installment, or part B, of a video lecture on section 3.1 of the textbook, and we are considering matrix operations. If you'll remember, in the first part, or part A, we covered some matrix terminology, the adding and scaling of matrices, and matrix multiplication. In this installment, we'll look at partitioned matrices, matrix powers, and matrix transposition. So let's begin with partitioned matrices. Let's look at the matrices P and Q that are before us on the slide here. Notice that they're both 4x4 matrices. And so I know that they're conformable with respect to multiplying P times Q or Q times P. So let's imagine that the problem before us is to multiply P times Q, P on the left, Q on the right. Now, one thing we can take advantage of is the fact that P and Q both have pretty special forms here. Notice that I can divide the matrix P in half in both directions, and I can reveal some 2x2 submatrices. Two of them are very simple. I've got this 2x2 matrix of zeros here, and I've got a 2x2 matrix of zeros here in this quadrant. So that's a pretty special feature of P. Notice that Q has kind of the same feature. Here I can split it in half in both directions. I can see these 2x2 submatrices on what we might call the main diagonal, and I'm seeing this matrix of zeros in both of these other quadrants. So in some sense, we can step back and kind of look at P. I can recognize this matrix P as composed of a 2x2 matrix A, a zero matrix, and another 2x2 matrix I'm calling B. So here's the matrix A, and here's the matrix B. So I'm thinking of P as almost a matrix of matrices. Okay, and I can do the same thing with Q. I can see that it's going to have a matrix C, a zero matrix, and once again you'll see, because of the special form of Q, that the matrix C is also appearing there in that position. So again, Q can be thought of as a matrix of matrices. Now what I want to show you, and this will be easier to show than it will be to tell you, I want to show you how we can multiply P and Q together using what's called block multiplication. All right, so we can almost treat the multiplication of P and Q as, at first, a multiplication of these as 2x2 matrices, and then a second calculation of sub-matrix multiplication. So this will make more sense once we go to the document camera and work out the details. But this procedure is called block multiplication. All right, welcome to the document camera. We're going to work out this problem, the multiplication of P times Q, using our block multiplication strategy. And the idea was this. We noticed that the matrix P could be partitioned into some 2x2 submatrices. We can identify this part as A, that's a 2x2 matrix. We can identify this part as O for this zero matrix, another zero matrix, and then in this quadrant, we'll call that matrix B. The matrix Q also has this nice division into a 2x2 matrix we'll call C, a pair of matrices which we'll identify as the zero matrix, and the matrix C again in this quadrant. So our idea is to multiply P and Q together, but first, in some sense, formally by multiplying these as blocks of 2x2 matrices. So let's see what that would look like. So if I want to multiply P times Q, I can first think of them as 2x2 matrices being multiplied together. I want to show you formally what these parts look like. So when I multiply these together first as 2x2 matrices, I've got A times C plus 0 times 0. In this position, I'll have A times 0 plus 0 times C. In this position, I'll have 0 times C plus B times 0. And then finally 0 times 0 plus B times C. Now what we'll find is that anytime I'm multiplying by 0, whether it's on the left or the right, it's always going to be the zero matrix. So This is going to be 0, that's 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 going to be 0, and that's going to be 0. So what we're left with, the only pieces that are of any significance left, in this position I'll have a times c. This will be 0, this will be 0, and this will just simply be b times c. Now, once you get very comfortable with this, you'll very quickly be able to go from here to here. So you can save yourself this intermediate step. But this block multiplication basically allows us to leverage all of the zeros that are sitting in these quadrants. And very quickly we can move from this to this. Now, all we have to do is carry out these 2 by 2 matrix multiplications. Now we break down into the 2 by 2 subblocks and do these calculations. So we still have to carry out the calculation of a times c, and we have to calculate b times c. So let's carry out those 2 by 2 sub-calculations, and then we'll bring them back to get our final form for p times q. So let's do a times c down here. Okay, so we're going to have 8 minus 7, that's 1. We'll have negative 4 plus 4, that's going to be 0. 14 minus 14, that's going to be 0. And then negative 7 plus 8, negative 7 plus 8 is going to be a 1. So we know what to put in there. It's going to be this 2 by 2 matrix here. Now we have to carry out b times c. Let's look at that calculation. We know the result's going to be 2 by 2, and we just have to carry out the dot products here. We're going to have 2 plus 0, so that's going to be 2. We'll have negative 1 plus 0, negative 1. We're going to have 0 minus 21, and then we'll have 0, 12. Okay, so that's the product b times c. Now all we have to do is bring these back and write out the final form of p times q. So in this quadrant, I'm going to have all zeros. In this quadrant, all zeros. This is the result of the a times c multiplication. And this is the result of the b times c multiplication. And that's how we could carry out this multiplication using this idea of block matrices. Now, in this particular example, it's not clear that this was any faster, right? It's not clear that this was any faster than simply putting them next to each other and multiplying them as dot products of vectors of length 4. But as a theoretical device, as a kind of a way of thinking about matrix multiplication, this is very powerful. So the great utility of this method is often not in the practical realm, but in the theoretical realm. So I just wanted to show you how we could partition matrices into blocks and then carry out an overall matrix multiplication by first thinking of them as multiplying the matrices in blocks and then carrying out all of the block calculations and then pulling them back into the main calculation. So let's go back to the class notes and continue. Our next topic is matrix powers. So let A be a square matrix, and I'm emphasizing the word square here because everything we're saying on this slide would only pertain to a square matrix. So let A be a square matrix and let K be a positive integer. Then the kth power of A is the matrix I obtain by simply multiplying A by itself K times. And we're going to denote that by A with a superscript of K. So for example, A squared is simply A times A, and A cubed is simply A times A times A. Let's work a problem together. Let's let A be the matrix that we see before us here, and let's find the fourth power of A. So join me at the document camera to work out the fourth power of this matrix A. All right, welcome back to the document camera. We've got our matrix A, and we want to find the fourth power of A. Let me suggest the following method. Let's take A times itself first, so let's find A squared. And we simply have to juxtapose the matrix A with itself and carry out that matrix multiplication. So we're going to get 4 plus 3, or 7. 6 plus 6, 12. 2 plus 2, or 4. And 3 plus 4, which is 7. So there's A squared. Now to get A to the fourth, we could imagine multiplying A times itself 4 times, but it's much more efficient to now take A squared and multiply it against itself. So we can simply take the matrix we found and do another round of matrix multiplication. Okay, let's see what we get when we do the multiplication. We're going to have 49 plus 48, and that's going to give us a 97. We'll have an 84 and another 84 together. That will give us 168. We're going to have 28 plus 28, which is 56. And then finally, 48 plus 49, which gives us 97. And that's the fourth power of A. Now, this does suggest that it pays to think ahead a little bit before you start wildly doing matrix multiplication, especially if you have to compute a larger power of A by hand. So let's think about what we would do if we had to work by hand, and let's say we had to compute the 10th power of A. So let's think about the powers of A that are relatively, well, I say relatively easy to compute. So A, I can do A times A, I can get A squared. I can get A squared times A squared, A to the fourth. By multiplying A fourth times A to the fourth, I can get A to the eighth, etc. So in some sense, the powers that are relatively easy to compute just by doubling the previous case are these powers of 2. So you can imagine that what you want to do to compute A to the 10th is to try to collect some powers of 2 that add up to 10. In this case, I can see that A squared and A to the 8th together will give me A to the 10th. So if I really had to do this by hand, and I had to compute A to the 10th, I would go for A squared times A to the 8th. And so how many multiplications would I have to do? I'd have to do 1 to get A squared, another 1 to get A to the 4th, another 1 to get A to the 8th, and then finally I'd have to do that product. So I'd have to do 4 multiplications to get to the 10th power of A. I don't have to do 10 multiplications, I just have to do 4 multiplications. So you get the idea. So think before you start computing powers, think about what's your most efficient way to get, in this case, the 10th power of A. All right, let's head back to the class notes and continue. Our final topic is matrix transposition. The transpose of an M by N matrix A is the N by M matrix denoted by A superscript T. So this represents the transpose of the matrix A, obtained by interchanging the rows and columns of A. So that is, the ith column of the transpose is merely the ith row of the original matrix A, and this is true for all I. So another way to think about this is looking at this example. So take a look at this matrix A. It has 3 rows and 2 columns. The transpose is going to have the opposite. It's going to have 2 rows and 3 columns. And how can I think of it? Well, let's think of it first this way. This first column of A is going to become the first row of the transpose of the matrix, and this second column of A will become the second row of the transpose of A. Another way to think about it is in terms of rows. the first row of A will become the first column of the transpose, etc. So really, what is a transpose? We're merely interchanging the rows for the columns, right? The rows become the columns and the columns become the rows when I pass from a matrix to its transpose. So the definition of the transpose of the matrix allows us to very easily define what's called a symmetric matrix. And the symmetric matrices form a very important class of matrices. So let's take a look at this definition and get familiar with the idea of a symmetric matrix. So a square matrix is called symmetric, right? So the matrix A is called symmetric if its transpose is equal to itself. In other words, A equals A transpose. So if I want to test to see whether or not a matrix is symmetric, in principle, it's quite easy. I can take the matrix A, let's say it's given to us, it's this 3 by 3 matrix. I can form its transpose, so I can interchange its rows and columns, and then I can just check to see if the matrix is equal to itself, if it lines up with itself element by element. Okay, so that's one way to think about it. But another way to think about this is to think about what that condition of symmetry is forcing. It's basically forcing Aij to equal Aj in every single pair of positions I and j. And what that means geometrically is something like this. If I take the matrix and I imagine folding it along its main diagonal, it should fold onto itself. In other words, the -1s in this case are folding onto each other, the 5s are folding onto each other, and the 8s are folding onto each other if I were to fold along this main diagonal. And that's often visually the idea of symmetry. You'll be able to see it in the matrix just by seeing kind of this symmetry along this main diagonal. So oftentimes that'll be the first glimpse that a matrix is symmetric, because you'll see that symmetry along that main diagonal. All right, now that brings a close to what I wanted to show you here in this first section of Chapter 3. So Chapter 3, Section 1 is completed. And I will see you once again for another video lecture on Section 3.2, so join me for that. Until then, take care.